Astronomy is the study of the universe, the study of its structure and its behavior. From our home on the earth, we look out into the dim distances, and we strive to imagine the sort of world into which we are born. We are confined to the earth. Our knowledge of outer space is derived from light waves and other radiations, which come flooding in from all directions. From time immemorial, men studied the heavens with their unaided eyes. Finally, about 3 centuries ago, the telescope was invented. With the growth and development of these giant eyes, the exploration of space has swept outward in great waves. Today we explore with a telescope 100 inches, that is more than 8 feet in diameter. It has the light-gathering power of more than 200,000 human eyes. We observe a volume of space so vast that it may be a fair sample of the universe itself. Men are already attempting to infer the nature of the universe from the study of this sample. The explorations fall into 3 phases. The first phase led long ago to a picture of the solar system, the sun with its family of planets, including the earth, isolated and lonely in space. Then, after several centuries had passed, a picture of a stellar system began to emerge. This was the second phase. The sun was found to be merely a star, one of several thousand million stars, which together form our stellar system, a swarm of stars drifting through space as a swarm of bees drifts through the air. From our position within the system, we look out through the swarm of stars, past the boundaries, into the universe beyond. The conquest of this outer space is the third and most recent phase of the explorations. The outer regions are empty for the most part, but here and there, scattered at immense intervals, we now recognize other stellar systems comparable with our own. These stellar systems, these lonely, drifting swarms of stars, are the true inhabitants of the universe. They are so remote that, in general, we cannot distinguish their individual stars. The swarms appear merely as vague, cloudy patches of light, and were called by the name nebulae, the Latin word for clouds. A few of the nebulae appear large and bright. These are the nearest swarms. Then we find them smaller and fainter, in constantly increasing numbers, and we know that we are reaching out into space farther and ever farther, until, with the faintest nebulae that can be detected with the greatest telescope, we reach the frontiers of the observable region. This glimpse of space, thinly populated by drifting swarms of stars, has been revealed by great telescopes, and in particular by the greatest of all those in actual operation, the 100-inch reflector of the Mount Wilson Observatory. It was the 100-inch that first detected individual stars in a few of the nearest nebulae, and identified among them several types of stars that are well known in our own system. Since the real brightness or candle power of such stars had already been measured in our system, their apparent faintness indicated their distances and, consequently, the distances of the nebulae in which they lay. Once the essential clue of the distances was found, the mystery of the nebulae was quickly solved. They are, in fact, huge stellar systems like our own system, and they appear small and faint only because they are vastly remote. Some nebulae are giant systems and some are dwarf systems, but the range in candle power is not great. For statistical purposes, they can all be considered as equally luminous. Therefore, their distances are correctly indicated by their apparent faintness. This property has been used to survey accurately the whole of the observable region out as far as telescopes can reach. The scale of the survey is so immense that a special unit of distance is employed in the reports. This unit is the light year, namely the distance light travels in a year, going at the rate of 186,000 miles each second. The number of miles in a light year is 6 million million. In other words, 6 followed by 12 ciphers. Light reaches the Earth from the Moon in about 1 1/3 seconds. from the Sun in about 8 minutes, from the nearest star in about 4.5 years. This last figure is typical. The average distance between neighboring stars in our own system is several light years. The diameter of our system, which is one of the giant nebulae, is about 100,000 light years. The faintest nebulae that can be detected with the greatest telescope are, on the average, about 500 million light years away. We intercept and photograph today the light which left these stellar systems far back in a remote geological age. This light has been sweeping through space for millions of centuries at the speed of 186,000 miles each second. Truly, as we look out into space, we look back into time. With the largest telescope, we can look out into space about 500 million light years in all directions. Thus, the observable region is a vast sphere about 1,000 million light years in diameter, with the observer at the center. Throughout this sphere are scattered about 100 million nebulae, each a stellar system at some stage of its evolutional history. These nebulae average about 10,000 light years in diameter and about 100 million times the brightness of the Sun. The average distance between neighboring nebulae is about 2 million light years. A rough model of the observable region might be represented as follows. Assume that the sphere, 1,000 million light years across, is reduced to a sphere with a diameter of 1.5 miles. Then the 100 million nebulae are reduced to the size of golf balls, and they are scattered through the sphere at average intervals of about 30 feet. On this scale, the Earth could not be seen with a microscope, not even with an electron microscope. The nebulae are scattered singly, in groups, and even in clusters, but this irregularity is a minor detail. When very large volumes of space are compared, they are found to be remarkably alike. On the grand scale, the observable region is very much the same everywhere and in all directions. In other words, it is homogeneous. This feature could not be predicted. It is the first characteristic definitely established for our sample of the universe. Only one other general feature has been found. Light reaching us from the nebulae has lost energy in proportion to the distance it has traveled. The fact is established, but the explanation is still uncertain. The problem thus posed, which involves the possibility of an expanding universe, makes an exciting story in itself. It is mentioned now merely to complete the description of the observable region as known today. To summarize, the explorations of space have swept outward in 3 waves, through the system of the planets, through the stellar system, into the realm of the nebulae. In the first phase, the Earth was found to be one of the family of planets which circle the Sun. In the second phase, the Sun was found to be one of the millions of stars which make up our stellar system. In the third phase, our stellar system was found to be one of the millions of nebulae which are scattered rather evenly through the region of space that can be observed with telescopes. The next step involves some guesswork. We suppose that the region we have explored is like any other large region of space, that the observable region is a fair sample of the universe. With the aid of this assumption, we may discuss the universe on the basis of factual knowledge. Men are already assembling the types of possible universes which are consistent with the known facts. As more facts are discovered, the number of such universes will steadily decrease. Thus, step by step, we may hope to discard the possibilities and finally recognize the universe we actually inhabit. The venture stirs the imagination profoundly. It has become feasible only in our generation. With the aid of great telescopes, we have at last won our way beyond the stars of our system, out into the very depths of space. The explorations will continue. still greater telescopes will be put into operation. And slowly, as the darkness recedes, the universe will loom forth.